Good evening, ladies and gentlemen. Welcome at the 24th instance of the expert lecture series of the Vice Chancellor at the University of Pretoria. My name is Prof Erasmus. I'm the Dean of the Faculty of Natural and Agricultural Sciences. At the moment, most people refer to me as the new Dean because I'm, I think, 36 days on the job. A few housekeeping arrangements. In the event of something wrong, which I hope won't happen, follow the green signs as you go out, exit on the right side onto the grass, and in the passage on the left-hand side are the bathroom facilities. Events like this gives me great pleasure to see that in addition to the excellence in research, teaching and learning that happens at the University of Pretoria that is relevant to the problems on the African continent, we also punch above our weight on the global stage. It gives me great pleasure to introduce the Vice Chancellor and Principal, Professor Kupe, for a short message and a formal welcoming. Professor Kupe, thank you.
Very good afternoon, ladies and gentlemen, and thank you, Professor Erasmus. You can tell that Barren came from where I'm not as new as he is, but I'm not yet 12 months here. You can tell Barren and I came from the wrong place where we don't understand protocol. So he jumped protocol, and there are important people sitting here. So I'm going to try the protocol thing, but it will be quite disordered. I can't blame where I came from on the basis it was the person in some ways. But I would like to recognize the members of the university's executive. I see Professor Anton Stroh here. He actually had something to do with Roger Deane being here, so I think it's important to mention him in this context. I don't see my other colleagues, but in case they are hiding, I acknowledge you. Then deans of faculties, I saw a dean of another faculty, Professor Vasu Reddy, directors, senior managers, professors of the university, academics from across the university, alumni, and students. As you know, the Vice Chancellor's Expert Lecture is an intellectual event meant to be shared with the university community, as well as the broader public at large, including our alumni. I think a university is not a university without the kind of intellectual sustenance that is not only limited to lectures, seminars, and conferences, but that which is shared with the generality of the public. Breaks down the boundaries. It also demonstrates to society that the university is part of society and not apart from society. Today, I have the pleasure of presenting Professor Roger Deane as the Vice Chancellor's Expert Lecture person who will deliver it. Roger Deane is an associate professor at the University of Pretoria, where he established the radio astronomy research group, and that is where Prof Stroh is implicated in that intellectual crime, which is a good crime indeed. He completed his doctorate at the University of Oxford and returned to South Africa after being awarded the Square Kilometre Array postdoctoral fellowships at the University of Cape Town and at Rhodes University, followed by the position of Senior Research Fellow at Rhodes University. He subsequently moved to the University of Pretoria in 2018. His research interests cover a broad range of energy and spatial scales, from diffuse neutral hydrogen galaxies to the inner accretion disks of the supermassive black holes. He's especially interested in binary supermassive black hole systems, strong gravitational lensing, and black hole shadow imaging with the Event Horizon Telescope. He places a large emphasis on matching scientific objectives with the appropriate technical expertise, specifically in observational methods, probabilistic Bayesian analysis, and increasingly machine learning algorithms. These approaches have become progressively more important in exploiting the power of next-generation radio telescopes, such as South Africa's MECAT radio telescope. As you know, that is the precursor to the Square Kilometre Array, and the Event Horizon Telescope. Ladies and gentlemen, I have a long CV of Professor Roger Deane. We have to make an intelligent choice tonight. I can read all of these pages, and then there will be very little left for the expert lecture. I'm not the expert tonight. Ladies and gentlemen, please, let's clap our hands for the expert tonight, Professor Roger Deane.
Well, thank you very much for that very kind introduction, Professor Cooper, and indeed for the invitation to present this, the Vice-Chancellor Expert Lecture number 24. Thank you to all of you for attending. It's not the easiest time within the university calendar to attend a talk such as this, especially to the youngsters, the students who got exams. That's impressive that you've taken your time out there. And then, of course, the Springboks have just returned from World Cup victory in Japan and have just landed at OR Tambo a few hours ago, so we could have been there as well. Instead, you're here to hear about black holes, and this is a simulated image of a black hole. We think we captured an image of the real thing earlier this year that was released on the 10th of April, and this presentation is going to take you a little bit through that. Our key point is that my name's on the left there, but this is really on behalf of a very large team spread across the planet. So this is very much on behalf of the Event Horizon Telescope collaboration. A photograph of which you see there, that's not everyone, but the vast majority of us at our collaboration meeting at the end of last year, where we had a very big secret, and we weren't allowed to tell anyone. But the image was, so to speak, in the bag at that point. And this team is just the most extraordinary group of people I've met, with expertise ranging from engineers who build telescopes, who improve the actual surface of a telescope, right through to the data analysis right at the end of that, looking at imaging algorithms. Bayesian parameter estimation was mentioned in the introduction. I was impressed with that. So a full suite of expertise across the board that really is necessary to achieve this result. I'd also like to acknowledge the stakeholder institutes, 13 of the logos of which you can see over there. And then, of course, there are associated institutes, of which the University of Pretoria is, let me just point out, apologies to the people online, the University of Pretoria amongst some of the most prestigious institutes on the planet through this project. Now, the image that was released, I'm sure many of you have seen it, this orange glow, which I'm going to be diving into a bit more detail. It grabbed people a lot more than the collaboration expected. Just 2 nights ago, the result was awarded the Breakthrough Prize for Fundamental Physics, so-called Oscars of Science. And you can see Mark Zuckerberg awarding the prize there. Very odd. I mean, this is the only event where you will find our finding director, Shep Dolman, at the same, well, all respect to Shep, but at the same event as Lenny Kravitz on the right there. But a remarkable recognition, and something that I think most did not anticipate. I mean, it was on some of the more major newspapers on the planet, many of them. And then perhaps the most interesting aspect to all of this was the internet memes that resulted. Some more politically correct than others. Perhaps I should change very quickly. But all told, it's expected that, well, estimated that more than 1 billion people saw this image, which is not what most of us, I would say, expected. That's just extraordinary, 1 billion people. So the question naturally goes, why? I mean, we were working on our experiment trying to image this black hole, 55 million light years away, working on it, spending a lot of time in front of a computer, coding, and then releasing this on the 10th of April. And I guess, people can debate this in detail, but I guess it's just because it represents this sort of edge of the universe. That is, that inner boundary, that the inner part of that ring is an exit point to the universe. This is one of the extreme objects in the universe. And it's represented in a photograph, something that we can immediately relate to. And yeah, we were blown away. Now, in this lecture, I want to just step beyond all the superlatives and all the internet memes and all the, hype, so to speak, and tell you a little bit about what's behind the curtain. What does this image actually represent? And what is some of the work that went into actually producing it? So the first question is, well, how do you take a photograph of something from which light cannot escape? Fair question, and beautifully illustrated here in a simulation by colleagues of ours at Radboud University. What you're seeing there are two emission components. The orangey stuff is an accretion disk. Think of water flowing down the plug in a basin. And the jets are emission that is being accelerated close to the speed of light. So it's an extraordinary object. And the answer is you don't image stuff coming out of the black hole, but these very energetic phenomena in the immediate vicinity of the black hole. It's the accretion disk and these jets traveling close to the speed of light on either side. More of that later. In talking about the shadow of a black hole, which is what we image, I need to tell you a little bit about the size of a black hole. So this is the distance at which light cannot escape. If you look up a black hole on Wikipedia, for example, that's the standard definition that's given. And this is known as the event horizon, which is the reason for calling our telescope the Event Horizon Telescope. And it turns out the size, the characteristic scale of a black hole, is only dependent on the mass and the spin of the black hole. That's within a general relativistic framework. There might be other theories that prove to be right, but if we believe general relativity, it's just those two parameters that define the black hole. So the analogy I like to use is the Niagara Falls, which my postdoc and I we were quite close by there at the Perimeter Institute at an EHT workshop just recently. Now, the Niagara Falls, if you go closer to the edge, obviously the water flows faster and faster until it goes over the edge. And the size of a black hole can be likened to that distance from the edge of the waterfall at which you swim at your maximum speed and you stay still. You just can't escape, you just don't go closer. Now, the analogy with the black hole is it's not you swimming, but rather a photon of light that is trying to escape. And space-time is actually falling into the black hole because of this gravitational well. And that defines the size. Now, if the black hole is not spinning, it's called the Schwarzschild radius. Carl Schwarzschild came up with the solution just within a few months of the publication of Einstein's general theory of relativity back in 1915. Okay, so that's the size of a black hole. And I'll come back to Carl Schwarzschild a little bit towards the end of the presentation. So that's the characteristic size, this distance at which light can no longer escape. So what then is the shadow that we keep talking about? And to explain the shadow, which I'm going to do in two lovely graphics that have been produced, I need you to keep two concepts in your mind. The first concept is light bending around this black hole. It's distorting space-time so much that there are these huge deviations of light bending around the black hole, or appearing to bend around the black hole. The second is light being captured by the black hole, going into the inner ring of that orange ring and disappearing outside of our universe. There's no way that photon can come back out and hit our telescope or the back of our eye. So with that in mind, those two concepts, have a look at this simulation where you see some photons far away from the black hole, obviously just continuing on. But if they come quite close, they are deflected at increasing angles, and some of them get so close that they actually orbit around the black hole. Space-time is orbiting around the black hole. So you get this light enhancement, a ring around the black hole, and then a very clear deficit where there are no photons coming from because they've been captured by the black hole. And that's the simulation and the image that we saw, that we released earlier this year. All right, so I looked at it another way. If you're going through this disk of material that is slowly heating up and swirling around the black hole as it falls in, you would see this definite feature of brighter emission, then going to a sharp decrement, which is the shadow of the black hole. So if we go back to that beautiful simulation by Jordi Davila from Radboud University, here is a still of it on the far left there. The very inner part of that is what the Event Horizon Telescope image that we released earlier in this year. You can see that the southern part is brighter, and that's because, remember, in that movie, the gas is swirling in, and towards the southern end, it's swirling and traveling towards us at relativistic speeds, close to that of light. So what happens then is that light is brighter compared to the light that is on the northern side of the ring, which is traveling away from us, so it is dimmed. And that's why you see that asymmetry in the ring. All right, so we've talked about the characteristic size of a black hole. We've talked about what the event horizon, what the shadow is. We're now going to talk a little bit of the instrument and how you actually take a photograph of this, this feature that was predicted. So the first thing is, to borrow an internet meme, one does not simply take a photograph of a black hole. You don't just point and shoot. What we use is actually an Earthsized telescope, as the title suggested. Except we don't have glass covering the entire telescope. We've got tiny shards at very specific points on the planet. So this is how we liken the network of telescopes that we synthesize to create one telescope. Little pieces of glass that we then stitch together using software. So we don't have the collecting area of the globe, but we have pieces of glass as far as possible as we can put on the Earth. And the upshot of that, the reason we do that, is the further they are apart, the finer the detail we can make out in whatever object we are studying. So the further apart the glass, the smaller the pixels in the image that you would make. Now, an example that I use for my third-year observational astrophysics class here at UP is, here is this, the Humanities building here at the University of Pretoria. As Professor Stroh will well know, if you take a 2D Fourier transform, but just think of that as an abstract mathematical representation of that building, it incorporates all that information. So you can go back and forth between left and right as much as you like. There's no loss. But what this interferometer does, with antennas spread across the globe, tiny shards of glass just capturing some of that signal, is it collects parts of that. It samples parts of that abstract mathematical representation. And then we try and reconstruct the image as best we can. And on the left there, you can see, to some extent, you can see the Humanities building. It's not perfect because we've lost a lot of information because we don't have shards of glass spread across the planet. But that which we did collect, we can actually reconstruct to some extent what we see. You can see that the building is there's a far better representation of the building rather than the students in the front of the building. Perhaps if we change the positions, well, we know if we change the positions of the shards of glass, we might be able to recover the students there a bit better. All right, another key point is that the EHT uses both the extremes of the universe. We put the shards of glass as far apart on the planet as possible, but we put them in very specific positions on the planet. All right, so we use the extremity and the extremes. And to illustrate that, you can see some of the locations of these antennas. Beautiful sites. Hawaii, on a volcano 5,000 meters high. In the Andes in Chile, also at about 5,000 meters. The South Pole. That's not your average passenger aircraft landing at the South Pole on the bottom right there. And you have to go to these special sites because they're very dry. You basically have to get above what is known as the troposphere. Precipitable water vapor content in the atmosphere basically absorbs our signals and it also scatters them. So it can basically blur out and absorb any hint of a black hole shadow that we detect. So it's very important that we put these sites. By the way, at the end of this video, you might see a K-Way jacket and someone who resembles me eating some pizza rather than working on the black hole. But anyway, just to prove that there's South African involvement in this project. Another big thing is that this data, even though there were only 8 stations involved in the image that was released earlier this year, it collects phenomenal amounts of data. So we'll come back to the square kilometer array in Meerkat that Professor Cooper mentioned in the introduction, but even this station, which only has very few shards of glass, is collecting in the 2017 campaign 4 petabytes of data. The raw data was 4 petabytes, and you can see some disks arriving at MIT Haystack that are ready to be combined with the signals that were recorded at other sites. So we don't connect, there's no high bandwidth connection to the South Pole, so we have to put these on these huge disks, and we have to put them on aircraft and bring them all together, and then stitch it together in software after the fact. Now, the thing that always concerns me, it makes me kind of wonder, what are we doing here? We started with 4 petabytes, and the final image is a few kilobytes in this case. It's not quite as extreme with Meerkat and SKA, but it's still pretty extreme. But it is interesting how much effort goes into those few pixels that you saw on the front pages of newspapers right in the beginning. So in a nutshell, we use the thing on the left to try and image the thing on the right. The thing on the left is this global network of antennas that uses the Earth's rotation. We need that Earth's rotation because that means our shards of glass effectively get placed in a different location as the Earth rotates. That process was awarded a Nobel Prize in the 70s. And we image this very, very hot gas, the apparent size of which is a donut on the moon. That was the image that you saw. And many analogies many superlatives, as I say, have been used to describe this. And I think one that really grabs us is the fact that you can fit the solar system inside of that black hole. It's a 6.5 billion times the mass of the sun black hole, squeezed into the size of less than a solar system. All right, but I'm going to move past superlatives, as I told you. I'm going to tell you a little bit more about what went into this. And the first thing that I like to tell people is that it's not just one image. One image seems like you're hanging in the balance. Well, not hanging in the balance, but the beauty about this experiment is you can do it many, many times. And it was done 4 times in 2007. There were observations that happened on 4 different days. April 11th, the one on the top there, is the day that we had the best weather and the most data. Everything really went right. Things went really right in the other days as well. But you can see that the structure of the image is remarkably similar to the April 11th. Now, there are some hints that there might be something moving. We wanted to be conservative in the first publication and just be sure about the image itself. But a big new focus is looking at the dynamics around that black hole. This is a really big black hole, 6.5 billion times the mass of the sun. That's on the upper end of the masses of black holes that we know, that we've measured, and that we expect from theory. So the evolution of that black hole is quite slow. We only expect things to orbit around that solar system on a timescale of months, rather than the few days separations that these images were separated by. But a big new focus is moving on towards that, and I'll come back to that towards the end. Another really impressive thing is that this image was made, it's not just 4 days, but we go for triple redundancy in the Event Horizon Telescope. Because it's just a brand new window on gravity and black holes, you want to be absolutely sure that things are working and are consistent with what you expect. So 3 different algorithms. The algorithm on the left, DiffMap, has been used for 40 years. The other 2 algorithms are brand new, bleeding edge, and these things give very, very consistent results. The images on the middle image, EHD imaging, and are on the right, Smiley, actually have a little bit more detail that you could see. But everything was blurred to that little white circle at the bottom right, just to be conservative in the beginning. But things will move on to looking at what the kind of substructure that is in there. Now, a big part that UP played is, great, you make these images, but you want to make sure you understand the instrument and the theory. So the EHT has a whole lot of black hole theorists that understand the very details of the physics of what's going on in the vicinity of the event horizon and predict what the shadow looks like. And on the top row there, you can see predictions from some of our collaborators, from our collaboration, on what the shadow actually would look like if you were right up there and you could see through radio eyes. So you can see it's remarkably sharp, but unfortunately you don't have the perfect instrument. It's a wonderful instrument, but it blurs that. And so what you see at the bottom, each of these bottom ones is actually corresponding to what it would look like through the weather that we experienced in the 2017 campaign. If the antennas wobbled in exactly the same way, if various instrumental properties were the same, and we modeled them as best as we can. And that's where UP's contribution, one of our main contributions to the Event Horizon Telescope, happened. So the fact that the bottom panel there looks remarkably similar to the image that we produced gives us a lot of confidence to first order in, A, that the black hole theorists are understanding what's going on in that vicinity, but B, that we understand the instrument in that, we put it through weather, things that are completely independently measured, and we get, putting it through our same calibration pipeline that is used for the real data, we get something that looks remarkably similar. Something I won't go into detail, but those different models are assuming different black hole spin. So the spin is orbiting opposite to the material that's flowing in the far left, and on the far right, it's spinning with it. And in the middle, it's what's known as a Schwarzschild black hole, and that's where the spin is equal to 0, and the size that I quoted earlier. So at this moment, things look remarkably consistent with general relativity for a whole range of different black hole parameters. For other reasons, we prefer the one which is highly spinning on the right, but I won't go into detail on that in this lecture. So I'm showing you orange rings, which I'm claiming are black holes. Let me just zoom out for a second and tell you where this lies in the galaxy. So the object, the black hole that we imaged is called M87. It lives inside what's known as an elliptical galaxy. This is a galaxy with about 10 to the 13 times the mass of the sun. And it's that haze in the center that you see of that image. That's how you see it through optical wavelengths, through what our eyes are sensitive to. Now, 55 million light years. That's fairly nearby in the cosmic neighborhood, but just to give you a sense of how that actually stacks up, this is a real-time photon traveling between the Earth and the Moon to scale. Let's do that for 55 million years, and that's how long how far these photons have traveled from that black hole to arrive on our telescopes, and then another 2 years for us to correlate and release the results. I'll black that out so that you don't feel like you're watching a cosmic tennis match, but roughly at the same scale, on the top right there, is how you would see M87 through radio eyes, not through what we see through our eyes. And you see a completely different object. What you see you see that linear feature right in the center there is the jet, very powerful jet, accelerating particles to close to that of light, the speed of light. And it stems from a black hole, which you can see on the bottom right, is the EHT image. So the range of scales here is huge. An analogy I like that's used for nanotechnology, if you're using that image on the orange image on the top right, if you're holding that in your hand, the black hole in the EHT image is on sort of at the atomic scale. So if you think about nanotechnology and the range of scales there, this is a remarkable object with a remarkable range of energies. So that's the host galaxy. Now, there are a whole lot of consistencies we have with the black hole. The black hole is basically the same mass as we expect from a galaxy of this size. There are a whole range of other consistencies that I won't go into, but there is a bigger picture to this black hole. We're not just zooming in on the black hole, but trying to understand it in its context. But a big next step on the image itself is actually trying to measure its circularity, or at least its deviation from a regular ellipsoid. And the key thing there is, if you want to test if Einstein's theory may or may not hold up, is you measure the circularity of that image. At the moment, it's consistent with Einstein's predictions, but as you'll see in the next few slides, we're going to be ramping up to try and make more stringent tests over the next years and over the next decade. Another interesting factor about that whole that shadow is as you change the position angle, remember this is a disk of material swirling into a black hole, as you change the position or the inclination of that, there is always a shadow feature because of this very strong bending of light in the immediate vicinity of the black hole. So we got lucky because the M87 black hole was fairly face-on and fairly ring-like, and that was optimal in terms of imaging and making out the shadow feature. If it turns to more edge-on, it'll look a little bit more like a crescent, and that'll be slightly harder, but there is also lots of science in that because then there is a bigger, what we call Doppler shift, but more on that later. Another thing I want to comment on, this is one of my UP master students working on, we want to, as we move from M87 to the black hole at the center of our galaxy, which I'll show you an image of, not a real image, but a simulated image in a moment, we're going to be making far more images. And the reason for that is the mass of the black hole in the center of our galaxy is about 1,000 times less. If it's 1,000 times less, the size of the black hole is about 1,000 times less. And that means it evolves on 1,000 times faster timescales. So rather than months, as I mentioned earlier, it'll be minutes. And so there are going to be lots and lots of images. And this is a simulation of the time evolution of the black hole. And what Michaela Menegaldo is working on is actually trying to self-organize different images based on different black hole spin parameters, different models for the magnetic field and the immediate vicinity of that black hole, and a range of other parameters. So you can see quickly how, if you're making lots of images, you want to be able to classify these very quickly in order to do your modeling, which is a lot more expensive. So even though we're studying a single object, things like machine learning are still very, very relevant. Okay, so as I move towards wrapping up, I want to talk a little bit about what's next for the EHT. There are 4 main things that we're working on right now. So obviously we'd like to repeat this experiment. We repeated the experiment 4 days in a row, and we got similar images. But we want to do that on year-long timescales, especially if the evolution of this black hole, M87, is of order months. So that's one of the first tests. But then we're moving to the lower mass black hole, which evolves on timescales of minutes. And there we expect that we should be able to make movies. And movies provide an incredibly, should provide a lot more stringent tests of general relativity. Part of the reason for that is we know the mass of the black hole in the center of our galaxy to far higher accuracy than the M87 black hole. Then we're looking at something called polarization. So if you think about using Polaroid lenses and looking at the sea and the scattered light is removed, that's can be thought of as an analogy just to give you a sense of what polarization is. And that's looking at preferred planes of light, which give us a lot of insight into the actual magnetic field structure in the immediate vicinity of the event horizon, which can tell us a little bit about how it feeds. And then a big thing is expanding the array. We had shards of glass on a few different positions on the planet. We want to put a few more, and we want to do so very strategically because these are expensive shards of glass. But I have a bias. You see a big gap on the African continent, and this is from an object that is what we call equatorial. The actual position of the black hole at the center of our galaxy is even further south, so that would expose the fact that there is even a larger gap to be filled in the southern hemisphere with telescopes in the southern hemisphere. So I think we're going to be working very hard at trying to get African sites, not just because of the obvious bias, but because of the huge potential that it provides in improving the imaging quality that we have with the Event Horizon Telescope. Now, on that note of African telescopes, a question I've got so frequently, and I'm sure might be on your minds, is were South Africa, we're building these wonderful telescopes in the Karoo that were mentioned. Were some of them used? And surely they were part of this amazing image that was made. And I'm sure all of you saw that Meerkat was inaugurated last year by the Deputy President. It is these 13-meter dishes spread across the Karoo, about an 8-kilometer diameter. Now, unfortunately, the design there is such that it cannot actually reflect wavelengths of light so short as what the Event Horizon Telescope observes. Another factor is it's simply not high enough. The Meerkat telescope and the Square Kilometer Array was selected at sites that were accessible but remote at the same time. Whereas clearly with the EHT, we have to go up to 5,000-meter volcanoes into the South Pole. We don't have that luxury. We have to get above the atmosphere. Meerkat can observe light from lower in the atmosphere. But one of the images that you might have seen following the inauguration was this beautiful image of the center of our galaxy. Again, you're seeing very energetic phenomena in the immediate vicinity, and right in the center of that image is a black hole, the much lower mass black hole that I described earlier. And this has been celebrated. It wasn't just hype. This is the best image of the center of our Milky Way at this frequency by a long way. and some very famous figures in front of this. And I think I'll show another famous image of President Ramaphosa, just given the opportunity. You could have also been at home watching the highlights of that wonderful game, so further thanks for that. So that image of the center of our galaxy that Meerkat made, which you might have seen in Nature, to the scientists, you might have seen it in Nature a few weeks ago. If you look at the Milky Way as this beautiful vista you see here from the Karoo site, that image sits not to scale, but roughly there. And if you had to look at that, the apparent size of the moon, which is roughly your thumb at arm's length, half a degree, is roughly that scale. So there's a whole lot of energetic phenomena that's happening in that immediate vicinity. But for scale, the black hole that we are next targeting, that we're trying to make a movie of, is a donut on the moon. So completely different scales. I think it gives you a sense of, just how different the Event Horizon Telescope and Square Kilometre Array and Meerkat are. Very, very different spatial scales, very different observing frequencies. But looking at very, very similar questions, trying to understand black holes and how they impact their host galaxies. The difference is that Meerkat is a wide field camera that will image millions upon millions of black holes, whereas the Event Horizon focuses on a select few, like an electron microscope, to try and disentangle what's going on in its immediate vicinity. Now, what's really exciting is that we really do stand on the precipice. I'm not going to make any promises. We're not sure when our next results will come out, but we're working very hard, I assure you that. But we do stand on the precipice of making black hole movies of the black hole in the center of this beautiful Meerkat image. And here's a wonderful simulation by Michael Johnson from Harvard, showing what we might achieve with 3 African stations. You're looking at real-time black hole physics. Look at the timer on the bottom left there. You're looking at timescales of minutes, making many, many images of one of the extremes of nature. I'm extremely, extremely excited and inspired for this next chapter. So in tying that up, I'd like to just sort of connect the past, look at where we are currently, and look to the future in terms of black hole physics. I'll take you back to Carl Schwarzschild, as I described, fighting on the Russian front, just having seen within a few months of Einstein publishing his general theory of relativity, deriving what would be the characteristic scale of a black hole, the Schwarzschild radius. And he wrote to Einstein and he said, "As you can see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." He would pass away a few months later, but just remarkably inspiring. But it would take quite a long time, despite that work, for black holes to be accepted in the scientific community. And a quote that captures that feeling: the shift happened in the 60s and 70s, and the famous mathematician Sir Roger Penrose, who Professor Stroh would know very, very well, this quote basically captures that change in feeling of, black holes should be abhorred and nature must conspire to prevent them because they create such a problem. He said he saw black holes change from a piece of mathematics, being a piece of mathematics, to something people actually believed in. Well, I think this, seeing is believing, and this image, I really think, takes us a long way to providing the first visual proof of the existence of black holes. Now, if I look to the future, that is my son reading his textbook on the 10th of April. My wife captured that image while I was in Brussels. The HT is this completely new probe of gravity. Nothing else does what it can do, which is hugely exciting. So these tests will become a lot more stringent. There has been a grant awarded by the National Science Foundation in the US of $12.7 million to expand, build what is called the next generation Event Horizon Telescope. So this is hugely exciting that this is going to be moving forward, making far higher quality images and measuring the degree to which that image is consistent with Einstein's theory and other theories. I think, questions that we can really think about is what role will Africa play in that in the next few years, in the next decade? And perhaps longer term, what theories might my son study? Will that textbook be obsolete in a decade or more? So with that, I'd like to thank you, to thank Professor Coupe for the invitation. I'd like to thank you all for making the time to come out here. I'd like to thank my wife for tireless support of my endeavors and obsessions. And I'd like to thank you all for attending.
Thank you very much, Professor Deane. From my side, thank you very much for unpacking a complex and complicated subject in a way that's visually appealing and striking. And I've heard shorter versions of your talk, and it's no less lucid. So thank you very much, and congrats for making this accessible. I'd like to open the floor for some questions. And if you do have a question, there's a microphone in front of you. If you lift the microphone, there's a green button, I think, which you press, and then the microphone will be activated so that we can hear your question. And also, by the way, stream live, as we are doing at the moment. So the floor is open for questions. Got a question in front here. Thank you very much.
I'm an economist. I know nothing about the stuff that you're talking about, but I'm curious, how did you decide on the colors that you use for a radio telescope image? Was that kind of popular culture and myth that caused you to choose those warm colors, or could you have selected anything else?
Yeah, it's a question I get a lot. So the color there is just the intensity of the image. It doesn't represent differential intensity, which is what we perceive when we see color. That green chair is more green than it is blue, therefore we see it as green. Here, the color of the image was just selected to be orange. It was consistent with a few of the other choices that were made by some of the people leading the imaging team. But all it represents is differential intensity, a different intensity. Now, what's interesting is, by sheer luck, and I thank Michael Johnson from Harvard for doing this, is the image used to represent the Milky Way with Meerkat is the same thing. It's just representing the intensity of the emission, or the brightness. So that just happens to be the same as the simulations in the EHD image. Fun fact.
Thank you very much. Anything else from? We've got 3 questions. Let's take 2, which you can answer, and then we'll get to the third one here, right at the back.
Okay, thank you so much, Prof. And please pardon me for not having the technical know-how of how this thing is going. But I would just like to know, I see that the U.S. is planning to invest close to $2.1 million on that, except for making movies. How does the project generate revenues and make money, so to speak?
Yeah, this is a question that Blue Skies Research constantly has to answer, and rightly so. You know, especially in a South African context where Meerkat is a 4 billion rand infrastructure for some astronomers. So one has to ask, what is the utility here? I have 2 answers to this. The first answer is Blue Skies Research and big new breakthroughs do open up billion to $1 trillion industries. They just do so on longer timescales. You might have used Google Maps to get here. If Einstein's theory wasn't around and you couldn't make the corrections to the GPS spacecraft that are guiding you to the Senate Hall, you wouldn't have landed up here because those corrections are significant. And you would have been maybe at Pretoria Boys High School or something like that. So GPS is a $1 billion industry, and it's only really possible through Blue Skies Research that led to understanding gravity in a better way. Another example is Wi-Fi. I use Wi-Fi all the time. What we would do without Wi-Fi? Wi-Fi was partly invented in an experiment that was trying to find exploding black holes. It was a protocol that was developed out of scientific necessity and developed in that way. So Blue Skies Research, if done well and if it's ambitious, in my view, opens up big industries later on. So maybe that's a bit of a cop-out to say, we'll pay you later, but I think that's been shown to be true over decades and over centuries. But I think it's deeper than that, right? The payoff is for humanity. When we released that image, all of humanity celebrated with that. And that's not as quantifiable and tangible, but it's there. Discovery and wonder is there, and it's for us to all enjoy. That image was released to humanity, and it's for all of humanity to own.
Thank you very much. We have another question in the same row, but yeah, thank you very much.
I'm just curious, thank you for the talk. How do you identify black holes when they look like the image up on top there and they can look like stars? So how do you first locate them and identify them?
Very good question. There's a lot of effort that goes into exactly that problem. It's quite obvious in some circumstances because there are different emission mechanisms, things that produce the light that comes to and hits our telescope from black holes or in the immediate vicinity of black holes versus, say, stars. And so we have many, many diagnostics that we can use to identify, okay, I think this is a star, I think this is just the stars in a distant galaxy or gas, or no, that is an actively accreting supermassive black holes. And part of that is just the energies involved. Things get really, really hot. They glow red hot in the immediate vicinity of the black hole. So that means that you have a whole lot of things shining up in a way that the most massive star just couldn't possibly do. So one of the key things that I didn't really discuss here is that you actually have to observe the wavelengths of light across the electromagnetic spectrum. I showed M87 in optical light and in radio eyes. There's a whole continuum. I'm sure you've seen infrared glasses, night vision glasses in movies, for example. You can probe different things in that way. And by building up that picture across the electromagnetic spectrum, you can dissect which object might be a black hole and which might just be stars or gas. Thanks. Nice question.
Thank you very much. I've got one question there, and then Prof Stroh.
Hi, Prof. Thank you so much for this talk. It's been super great of you to share your knowledge with us. So my question is very weird. Okay, so my understanding is that black holes differ in size or mass. Okay, so given the general theory, the theory of general relativity, you're focusing on new black holes now, and you want to take images of them as well. So do you expect to see differences, or do you expect them to look the same? And if differences, what type of differences do you expect?
So I'll give a little bit of background as to how we select these few black holes. They have to be a combination of really massive, because the more massive they are, the bigger they appear. And then they have to be as close as possible, because obviously something that is closer will appear larger on the sky. So there's a balance there. So our black hole in the center of our galaxy is actually not fairly average mass, just like the mass of our galaxy as well. It's fairly average. Whereas M87, the image that I showed today, that's a very massive black hole in a very massive galaxy. Now, we expect that if general relativity holds, we should see something similar. As I said, it'll be a lot faster because things evolve a lot quicker around a smaller black hole. But there are a few other complications as well. If you imagine the Milky Way as a fried egg, and we're in the egg white towards the periphery, the cosmic neighborhood, or the galactic neighborhoods, if you will, the black hole is right in the center in the yolk, and we're actually looking through the egg right to the center. That means there are a lot of electrons, free particles, charged particles, that are blurring out the light a bit. They're scattering the light in the way that, if you see a light reflected on ripples on water, it scatters in a similar way. And that could blur things out quite a lot. So the image that we recover might not look as beautiful as the image that we produced with M87, where everything's very slow and there's not as much gas in between us and the black hole. But it might hold even more scientific potential because things are so dynamic. Therein lies the challenge and the opportunity.
Thank you very much. Another question here.
Thank you, Roger, for an excellent presentation. How does the curve geometry actually relate to what you've illustrated here? The curve with almost his whole life on
Yes, so there are a few things there. So what Professor Stroh is referring to, the Kerr space-time, is not the Schwarzschild metric where you have a stationary black hole where spin is 0, but actually the black hole is spinning and it's dragging space-time with it, which affects the appearance of the image. So I showed a few images here. Let's get past the World Cup. Difficult to do. So I showed those 3 images on the top there represent 3 different metrics. One on the far left is where the black hole and the plasma falling in are anti-aligned. The Schwarzschild metric is around the center, and then the one on the far left and the one on the far right are Kerr metrics with a specific spin of the black hole. So the shape through these general relativistic magneto-hydrodynamic simulations, sorry, that's just what these are, I have to say it, you see different image morphologies, and things will change. And then also another interesting thing is that the dynamics, the plasma will change appreciably, which is one of the ways in which we disentangled. But that's not the whole picture. It's not just about the image. We have to combine it with other measurements that we make of this black hole at other wavelengths, as I was just referring to. So it turns out that we favor the image on the right here, a Kerr space-time with a highly spinning black hole, because the X-ray luminosity of this gas, photons of light going that are at a wavelength similar to that when you get an X-ray, the energies there require a highly spinning black hole, which is the Kerr metric on the right.
Thank you very much. Is there any other questions from the floor? We've got 2. Let's go at the back. 1, 2, and 3.
Thank you, Professor, for the floor. The EHT teams deserves all the praises in the world. But I have a very simple question, and I somehow kind of don't expect a simple answer. Why did the EHT team prefer to focus on the supermassive black hole of the M87 galaxy and not our own galaxy, which is the Milky Way galaxy?
That's not a simple question. That's a very good question. The predictions were that the black hole in the center of our galaxy, the apparent size of the shadow would be a factor of 2 to 3 larger than M87, which was released earlier this year. So in many ways, it was a better bet to go for the black hole in the center of our galaxy. But there are complications. It's a lot harder to make an image of something that's moving around. Picture, putting my 1-year-old son, making him sit there and say, all right, I'm going to take a long exposure of you. Just stay right there, right? The black hole in the center of our galaxy doesn't do that. It moves a lot. And that messes with the quality of the image that we can make. But then also the electrons that I mentioned, we were sitting in the egg white, these things blur out. So technically, it's a much greater challenge to image the black hole in the center of our galaxy. The other thing where we got really lucky, so M87, it's more of a ring than a crescent. It's more face-on. So that was easier to image. But also, the mass turned out to be a factor of 2-ish larger than we expected. So the shadow size was a factor of 2-ish larger than previous predictions could have made, which is an interesting result in its own right, which I didn't go into today. So as it turned out, M87 turned to be just better because it's a lot slower and there's less stuff between us and it.
Thank you very much. We have another one at the back.
Thank you for taking my question. It's a mix of 2 questions. We have Meerkat, and we're obviously able to image things like supernovas. Would we then theoretically be able to use Meerkat to find a supernova going off, and then the EHT to actually then document the formation of a black hole, especially the smaller ones, to then track the evolution?
So yeah, two questions. The first thing is that Meerkat has already discovered supernovae. They haven't just gone off, but they have, they're faint and they're very, very below the surface, and no other telescope picked them up. In fact, some of them are in that beautiful image that President Ramaphosa was standing in front of. So, it will absolutely do both. It will find old supernovae that it just has far superior imaging quality, so it can pick up diffuse faint features. Sorry, I'm just trying to find, there we go. So there are some supernovae in here, and above this image, there's a much larger version of this that was published in Nature a few weeks ago, where there are supernovae that previously were unseen. They're probably quite old. And then a big survey program on Meerkat is actually to find things that go bang in the night. Supernovae, there are a whole lot of other very, very powerful explosions that happen that are of huge topical interest at the moment, and Meerkat is supremely placed to discover those.
Thank you very much. We had a third question over there.
Hi, yeah, thank you for the lecture, it was lovely. I have two questions actually, science fiction enthusiast. The first is related to time. Is there a way to determine the age of this black hole that you've imaged? How do you do that, first of all? And then secondly, if we, hypothetically, were to get some kind of craft that was able to travel to this black hole and get as close as possible, what would that distance be before you do stuff like spaghettify and that kind of thing? So how close would we actually be able to get to this thing if we had the means to do that?
So to quickly answer the first question, it depends on the mass of the black hole. So the more massive it is, the less chance of spaghettification. And it's all to do with the tidal forces that are on your body. If they become so great that they can rip molecules apart, or at least tissue apart, they will rip you apart. And they are greater, that gradient is much larger for lower mass black holes. So for a supermassive black hole like this, you would go through the event horizon unscathed. You might get scathed later on, but that moment of passing through would be fine. Your other question is very interesting and a huge scientifical, that's a new word, a huge topic of research in astronomy is trying to understand how quickly black holes grow. The black hole that we observed, M87, is 55 million light years away. That sounds like a long way away, but that's basically present day in the cosmic age of the universe. That is about 13.8 billion years. And a problem that we face in astronomy is that we measure the masses of black holes that are roughly 1 billion years old. Well, they are 1 billion years after the Big Bang. And we measure very high masses, larger than the mass of M87. And we can't understand how the black holes feed quickly enough to get that massive. We don't understand how they could possibly start to be so massive, sort of 1,000 to 10,000 times the mass of our sun, and grow to that mass just 1 billion years after the Big Bang. We can use various estimates, so we can try and estimate how quickly material is falling into the black hole, known as the accretion rate. There's a lot of work into that. The problem is that can change quite quickly on the timescale of the life of a black hole. So this is indeed a huge challenge, and I don't have a clear answer for you because we're all working on it very, very hard, very actively at the moment. Thanks.
Do you have any other questions from the floor? Follow-up question?
Yes, I think I didn't say my first question correctly. It ties in with the previous question. Would we be able to use Meerkat and the new technology to capture that moment of the formation of a black hole, especially the lower mass ones, as you say, evolve quickly, so that that question can be answered, that evolution? Why do they grow so quickly?
I realize now that I didn't answer the second part of your question either. You would be able to see the explosion that happens following the death of a very massive star, a supernova. You would see the shock front because these are charged particles that then traverse magnetic fields, and what happens then is you have photons in the radio window, and a telescope like Meerkat would easily pick that up. Seeing the black hole afterwards with the EHT, which is the second part of your question, that would be a challenge and would depend on the black holes. But there would be a lot of things to consider there first. But it is something that is being considered within the Event Horizon Telescope. It wouldn't be able to set up quickly enough, I don't think, to see that moment of formation, but it might be able to follow it up. But it is some in the Event Horizon Telescope, not me, are looking at studying the other class of black holes, which are closer to the mass of the sun, rather than 1 million to 1 billion times the mass of the sun and live in the center of galaxies.
Thank you very much. Anything else? There's nothing from the floor. I'm going to use my privilege and ask a question myself. To what extent does limitations in storage and bandwidth speed limit what you envisage to happen next in this project?
So in terms of bandwidth, this is not a real-time experiment. We have to record on disks and move on. But already we're facing the challenge of, do we now delete the 2017 data that produced that image? That would be crazy, right? But we're running out of disks to record the 2020 session, which will come up in April next year. So yes, we're absolutely hitting these challenges because we're also upgrading the instrument. So the data rates are going to go up by factors of 4 to 16 in the next short while. So these are huge challenges. Once we start adding additional stations, things go up almost, it's a square. So we're going to have to be using we're trying to raise a lot of funding to handle this.
Thank you very much. Last call, not often that you have access to the expert himself. Let's take a last question from the back.
Prof, thank you very much for a very interesting lecture. Question, twofold as well. First, what is your time resolution on these measurements, if at all, seeing as you want to take videos?
That depends on a number of things. Primarily, remember you've got shards of glass on a rotating planet. As the planet rotates, it moves the apparent position of those shards of glass, and you need to fill as many, let me describe it. You need to make as many measurements as possible in that broken mirror. Make too few, you can't recover the image. You saw that terrible image of the recovered image of the Humanities building, for example. So it's a balance of how sensitive our images are, how quickly the black hole itself is actually moving, and how many actual shards of glass, apparent positions of them we need.
Okay, so given that, binary black holes, can you realistically image them soon, or is it just too complicated?
We are already trying. So there are a few sources that are not targeted for the fact that the expectation that we can actually image their shadows, but the EHT observes a bunch of sources that are interesting in their own right, and we can probe right down to event horizon scales and probe the jet launching that's going on. One of those sources is a very strong candidate for being a binary black hole. But the period is quite large. It's about 12.7 years. So you wouldn't need to image things on minute timescales, for example. Also, if you had a binary black hole at the center of our galaxy and it was so close that things were changing on the timescales of minutes, it's emitting so much gravitational radiation that it would quickly merge and become one. So we should be okay on that front, but it's an interesting question.
Right, thank you very much. I think let's bring it to a stop there. So that leaves the last part of my task to do a few thank yous. First of all, obviously, Professor Deane, thank you very much for once again unpacking a complicated subject in a way that people understand. And I think the engagement from our audience is testament that there's some real traction here. It's also great to see this level of excellence and this level of international engagement and participation for a university on the African continent. It shows again that we punch way above our weight. We tend to underestimate exactly what our global profile is. So thank you very much for being an example case, and hopefully there'll be many more to come. Thank you very much. Also like to thank the members of the exec. We know you've got full schedules, and my fellow deans. Thank you very much. UP staff, I know you also have full schedules, no less might be. And also the members of that are not from the University of Pretoria attending, thank you very much. We take the border community very seriously, and we know the role that UP plays in the border community, and we invite you to our next event when the time arrives. So thank you very much for that. An event like this doesn't happen with a lot of people around behind the scenes. Thank you very much to Lynette Smith for making all the arrangements to make this event happen. And there's also a whole range of security guards and caterers that make this possible. Thank you very much to them as well. And then finally, I'd like to come back to Tessa. As an academic, I know that this type of work and this type of excellence and this amount of travel to get this done is not without sacrifice at home. I'd like to recognize that and appreciate that. Thank you very much. That brings us to the end of the evening. Travel safely. Hope to see you again. Goodbye.